So now let's look at thermal conductivity. You know, in many ways, at least the way we describe it, there's parallels between electrical and thermal conductivity. So for instance, if this is our composite, and if this is our composite and it has carbon nanotubes in it, we can imagine that these carbon nanotubes, for heat to come from here and get transferred through this guy, polymers typically have very low thermal conductivity, and some nanomaterials have very high thermal conductivity. So in many ways, it's like polymers have low electrical conductivity, but carbon nanotubes have high electrical conductivity. The same approaches apply to electrical and thermal. And so basically, many of our equations are pretty much comparable, at least in the continuum mode. So we might say, okay, let's give it a try. Let's see if we can model thermal conductivity of composites, of nanocomposites, if like concepts of percolation threshold apply to thermal conductivity as well, or not, or why not. So I have imagine these are some particles in a matrix, and heat flow can happen in two modes, or a combination of these two modes. Like if I, for instance, take this region of the composite, or if I take this region of the composite, basically heat can come from this edge to this edge. It can go through the particle, and in this case, if I assume that the heat flow is mostly in this direction, then the temperature of this region and the temperature of this region are more or less the same, and the Q that goes, the heat flux that goes through this guy, is going to be the heat flux that goes through the nanomaterial and the heat flux that goes through the matrix. So in this case, these are parallel to each other. It's like that. But if I look, for instance, in a broader sense, if I, for instance, look between, if I consider from here to here, let me show it with the different colors so that it's better understood. If I consider from here to here, then it's not just this parallel region that work together, but I will also have for heat to go from here to here, from this surface to this surface. It has to go through a region that is primarily the polymer. So basically now, in this case, the temperature difference between this and that is equal to the temperature difference between this point and that point plus the temperature difference between this and that. And the heat flux through this and that are going to be the same. So this is the case of series, and that's the case of parallel. It's somewhere in between. For the series part, we can show that the conductivity is 1/, conductivity times of the carbon nan or filler times the volume fraction plus the conductivity of the matrix times the volume fraction of the matrix. This relationship, inverse relationship. And for the case of parallel is this. That's what we call the rule of mixture, basically. It's rule of mixture, it's average of the two based on the volume fraction. Now, the proof of these two are very simple. I expect you to know them, but if you don't, bring it up, and you can Google it easily. But if you don't, I can answer that. Now, I don't have any problem with this guy, okay, the parallel. But with the series, there's one thing that's very major, which we didn't take into account. That is the conductivity between filler and the matrix. That's what we call the contact resistance or the pizza resistance. It's a very important concept. And the reason behind that is that imagine I have two ropes that they have very different acoustic impedance. So when I vibrate them, when I vibrate one, some of the energy will go to two, but some of the energy will come back. And the reason for that is basically the phonons of one cannot couple with the phonons of the other. The phonons of one want to vibrate at certain frequencies that the other one doesn't. So some of the energy will be reflected back. And so that means there's some heat. You need to have a certain amount of, you will have a certain amount of drop in temperature. So if I plot the temperature change in this guy, the case that the heat flow is entirely this way, the temperature drop is going to be initially like a line because there's a heat flux here. At this point, there will be a jump. Then there will be another case. Then there will be another jump. And then it will be like that. So this part is because of the Kapitsa resistance. This is Kapitsa resistance. And there's this drop. And we assign a finite thickness to Kapitsa resistance based on molecular dynamics. Now, the origin of Kapitsa resistance is really a quantum physics phenomenon. It's not my expertise, but at least it can be a substantial amount, especially because the two materials like carbon nanotubes, for instance, or nanofibers and a polymer have very different elastic moduli. They have very different stiffnesses in the molecular scale. So the phonons, the natural frequency of the phonons is going to be very different. So basically now, because of that, we can modify this series effect and include the contact resistance. And now in this graph, they excluded the contact resistance. So they just found two bounds. One is the parallel model. The other one is the series model. Parallel model, as I explained, is called the rule of mixture. You see, all the experimental data are between the two because we're always between these two. But they're closer to the bottom one because of that Kapitsa resistance that I mentioned. And when you look to thermal conductivity as a function of volume fraction here or here, you don't see that trend that we saw in electrical conductivity. In electrical conductivity, it was like this, and it jumped. It was orders of magnitude. We don't see it here. We do not see it here. There are two reasons we don't see it here. One is the Kapitsa resistance, which messes up everything. Basically, it makes it harder for heat to go through the carbon nanotube because heat can find the least lowered resistance path, or a smaller portion of the heat will go through carbon nanotubes. The other reason that we don't see such a huge jump is because, if you go to the previous slide, the ratio of the conductivity of this to that is in the order of 1,000 to 10,000. In real cases, it's more in the order of 100 to 1,000 because carbon nanotubes have defects in them. But the ratio of thermal conductivity of electrical conductivity of carbon nanotubes to matrix can be 10 to 20 orders of magnitude. So we're talking about much more difference. And so adding a little bit of carbon nanotubes changes, or carbon nanofibers changes electrical conductivity much more than it changes thermal conductivity. So two factors here: the ratio of the electrical conductivities over thermal conductivities plus the computer resistance messes up and doesn't allow us to see that percolation threshold type curve. I'm going to stop here.